Here we're going to be looking at the Edexcel question FP2 on complex numbers from January 2010, question 4. In this question we have to find the modulus of z and the argument of z. We're going to use de Moivre's theorem to find the value for z cubed, and then we're going to find all the values of w such that w to the power 4 is exactly the same as z. So in this part of the question, we're given z, and we're asked to find the modulus of z to start with, which is a relatively straightforward task. The modulus of z is about applying Pythagoras to the given components of the complex number. And that gives us the modulus of z is exactly 16. The argument of z is a little bit trickier and we need to be more careful. The argument of z is often quoted as arctan y over x. But we can see, if we have a quick look at the Argand diagram, that there's a problem with that slightly simplistic approach. Real axis, imaginary axis, and z is approximately there. Its components are plus 8 root 3 and minus 8. Okay, so if we carried on with this simplistic formula, the y component divided by the x component, the method would give us the wrong argument. It would give us this negative argument. Clearly the argument we want is this positive argument, which is bigger than pi by 2. So we need to correct the answer, and we correct the answer by an additional pi radians. So we need to add on pi radians in this particular case. So it's always worth sketching the complex number to double check you've got the right argument. And then using your calculator, we'll get minus pi by 3 plus pi. So the argument of z, and this confirms what we suspected in the diagram as well, is 2 pi by 3. The mark scheme for this part of the question offers a B1 mark for simply stating the answer is 16 for the modulus of z, a method mark for correctly approaching the argument of z with the extra pi radians, and an accuracy mark for getting the answer 2 pi by 3. So in this part of the question we need to find z cubed, and it's very helpful to start off with the modulus argument form that we've just found in part A. Okay, so now when I look for z cubed and I raise this complex number to the power 3, I am then able to use de Moivre's theorem to produce a quick, efficient solution for z cubed. So z cubed is going to be 16 cubed, and then de Moivre's theorem will give me cos 3 times the angle plus I sine 3 times the angle, which tidies up a little bit to 4096 cos 2 pi plus I sine 2 pi, and then with the use of your calculator you can quickly get that cos 2 pi is of course 1 and sine 2 pi is of course 0. So z cubed is exactly 4096. The mark scheme for this part of the question offers a method mark for correctly applying de Moivre's theorem and an accuracy mark for the final 4096. In this part of the question, we're going to start with w to the power 4 is again z in modulus argument form. Except this time we need to make an adjustment to the argument. So before we go any further, we know that the argument of z is 2 pi by 3, that's called the principal argument. But in order to get 4 distinct solutions for w, we need to have 4 arguments. So we've got 2 pi by 3, and we get the other arguments by adding on multiples of 2 pi. Okay, where k is going to be 0, 1, 2 and 3. So by adding on multiples of 2 pi, the argument is intrinsically still 2 pi by 3, but it will allow us to get 4 distinct solutions for w. And it's w that we are particularly interested in. So now, when I take the 4 through to both sides, I'll get w is 16 cos 2 pi by 3 plus 2 pi k plus I sine 2 pi by 3 plus 2 pi k to the power 1/4. So de Moivre's theorem tells me that this will be 16 to the power 1/4 cos 2 pi by 3 plus 2 pi k all over 4. And there's de Moivre's theorem being used, plus I sine 2 pi by 3 plus 2 pi k all over 4. And now we can start to think about the different values of k. So I'm just going to tidy this up a little bit first. So I can get w is 16 to the power 4 is of course 2. Cos, and simplifying this angle a little bit, I can tidy it up to pi by 6 plus pi by 2k plus I sine pi by 6 plus pi by 2k. And now you might be able to see better why we needed the extra multiple of 2 pi. So now when we let k equal 0, 1, 2, 3, we'll be adding pi by 2 and another pi by 2 and another pi by 2 radians to each of our arguments. So we're going to get an equal distribution of answers around the origin, each pi by 2 radians ahead of the previous one. So now when I let k equal 0, I get w is 2 cos pi by 6 plus I sine pi by 6. And then on my calculator I'll get my first solution, which is w is 3 root 3 plus I. And likewise when k is 1, I will now get a distinct solution for w. And again I've tidied up the angles just to keep things as neat as possible as we're going along. So that will give me the second solution for w, which is minus 1 plus root 3i. And k is 2, we get the third one. And again, using your calculator, there's the third answer for w. And finally, remember we're only looking for 4 roots, so we can stop at k is 3. If I carried on with more values of k, I just get repetitions of the answers that I've just found. So I can stop at k is 3 And that gives me my final answer. So we've found all 4 solutions for W. And if I just do an extra little quick Argand diagram, you can see why we had to add on the extra 2 pi k. So when k is 0, I get the first, perhaps more obvious answer for W. When k is 1, I get the solution which is an extra pi by 2 ahead of that solution. So it's about there. When k is 2, I get another solution which is another pi by 2 ahead. And when k is 3, I get the solution there. And you can see that the roots form, in this case, a square centred on the origin. The mark scheme for this particular part of the question gives a method mark for the use of de Moivre's theorem and an accuracy mark for getting the solution for W when k is 0. However, it will give you the next method mark if you correctly dealt with the extra multiple of 2 pi, and the last 2 accuracy marks if you found the other 3 values of W, probably losing 1 mark for each mistake. You can find further support and material to help you out on the Further Mathematics Support Programme website.